Hey there everybody, this is Mr. Piercy, and this video is going to be an introduction as an investigation on what Taylor polynomials are. Taylor polynomials are going to be a tool that we will use to approximate either the behavior or of a function or the sum of a series, which, using a polynomial is typically going to be something that's more understandable, more approachable by a typical student than maybe the sequence or the function itself may ordinarily have been. So essentially what it's going to be is it's a tool to help us approximate sequences or series at certain values. It's not going to be something that we can use to approximate the entire behavior of the function, but more at a specific value. And that value is typically referred to as the center of the polynomial. In this case, what it's asking us to do, it says find the equation of a tangent line of y is equal to cosine at x is equal to 0. Now in this case, what they're doing is they're kind of illustrating that when we're saying x is equal to 0, this is what we're going to refer to as the center of the Taylor polynomial. Okay? If it had said something along the lines of any other number, that's what we would look at as the Taylor polynomial. Now, there's also going to be something known as a Maclaurin polynomial that kind of like Rolle's theorem. When we were talking about mean value theorem in AB calculus, we could say Rolle's theorem is essentially going to say there's going to be some value a between a and b that guarantees we're going to have a slope of 0, and that's specifically what we were focusing on. Well, Maclaurin polynomials are going to essentially do the same thing that Taylor polynomials do, but they're focusing on centers that are just going to be 0. So Taylor polynomials in general can have a center of anything, but Maclaurin polynomials generally are going to focus on things that will have a center at 0. Now, if you were to, I'm going to just go ahead, since we're talking about centers, I'm going to just go ahead and kind of give you a generic looking Taylor polynomial that you might see in a textbook, or if you go to a math website or something like that. You might see something that says something like C naught plus C sub 1 of x minus a to the first power plus C sub 2 times x minus a squared plus C sub 3 of x minus a cubed plus, and it'll just kind of keep going like that. Well, this value, the expression, whatever that is, set that expression equal to 0, that a value, that's what we think of as the center of a polynomial. So that would be a Taylor polynomial. A Maclaurin polynomial would basically be the same thing, just remove the a's. So it would be like c sub 2 times x squared plus c sub 3 times x cubed, omitting the minus a portion inside of the parentheses. What it's asking us to do, and again, I'm kind of getting off track here. It says find the equation of the tangent line to y is equal to cosine x at x is equal to 0. Oh, I don't want to restart my computer now. Let's wait for a little bit. There we go. And in this case, the slope of the tangent line at x is equal to 0 is going to be, let's see, something like this. I need to move that up just a bit. There we go, something about there. Okay. Find the equation of the line. Well, that equation would just be y is equal to 1. So we'll go ahead and put it here, I guess. Y is equal to 1. Sketch the linear, okay, I just did sketch the approximation. That's just that horizontal line there. And that is essentially what a Taylor polynomial is going to be. Now in this case, the Taylor polynomial is representing the line. In this case, it is a degree of 0 because it has no x value. There's no slope that we're going to have. This is just going to be a degree 0 polynomial, a constant expression. And as a tool to approximate the behavior of cosine, it's going to be pretty lousy because it doesn't look anything like it. It doesn't mimic it in any way other than the fact that at x is equal to 0, they happen to have the same slope of 0. And it doesn't really get much better. You're not going to really see a whole lot of approximation, a whole lot of similar characteristics between that constant line and cosine of x itself. So what it's asking us to do here, it says notice that our approximation does have the same y values and it has the same slope of the original function. I just mentioned that. What other property could be used so that it matches the point at x is equal to 0, meaning, of course, x is equal to 0 being the center. Well, in this case, the only other thing that we could use is we could look at the second derivatives test and understand that they could have the same concavity. Not can. The concavity will be the same. Now, because we're looking at a cosine function, if we were just going to kind of give a quick rough sketch of a cosine function, it's going to do one of these things here. A line is not going to demonstrate concavity in any way. So the next polynomial degree that we could look at that in any way is going to resemble the cosine function at 0 would have to be a quadratic. So when it says what degree polynomial would this approximation need to be, we're going to be looking at a second degree polynomial. We're going to have at least a quadratic polynomial, so that way we can kind of get any kind of thing that's going to resemble that shape of the cosine of x function at 0. Okay. So let's take a look here. How are we going to do that? What would the quadratic approximation be? Now, a lot of times what we think of, going back to just what we think of as the standard form of a quadratic, a lot of times going back to earlier algebra classes, we think of it being as ax squared plus bx plus c, okay? And we're going to kind of keep that same form, meaning the thing that's going to be similar for our Taylor quadratic approximation is that we're still going to go in the alphabetical order, A, B, C, D, and so on. However, what we're going to be looking at is going to be more in lines with what we would see here with the Taylor polynomial like that, where you can see the degree, the exponent values are not starting at the highest exponent value. They're actually starting at the lowest exponent value, and they increase as the Taylor polynomial gets bigger. So the way that I'm going to look at a quadratic with a Taylor polynomial, in this case, for a quadratic, I'm going to say the function f of x would be a plus bx, where we get to a first degree, plus cx squared, where now I'm at a second degree. And the function that we're approximating, of course, was y is equal to cosine of x. So if I take the first degree of the quadratic approximation, here I'm going to say f prime of x. In this case, the a goes away because the derivative of the constant is 0. And I'm going to have b plus 2c times x. And the first derivative of cosine, so y prime, would be negative sine of x. And then we'll go to a second derivative here. So f double prime of x will be, in this case, just 2 times c. And the next bit here, the second derivative of this one would be the derivative of negative sine, so that'll be negative cosine of x. What is the center of your approximation? Again, that was given to us at x is equal to 0. That is the center of the approximation. If they had said x is equal to anything else, we would have used that as the center of the approximation. Okay. So now what it's asking us to do, it says, well, what would the approximation be based off of what we're seeing in the previous table, or the table above? All right, well, let's go ahead and see what we might get here. Here, if I say f of 0, in the given function, well, b times 0 and c times 0 squared is just going to leave me with a. And if I do that with the given function y of 0, that's going to get cosine of 0 is going to give me a 1. F prime of 0, in this case, if I substitute 0 again for x into the first derivative, c times 0 is going to cancel out. It's going to become 0, and I'm going to be left with this b. But the first derivative y prime of 0 for negative sine of x, in this case, is going to be a 0. So here, f double prime of 0 is going to simplify to be a 2c, because we don't have anything to actually substitute. It's just going to be 2c. And here, y double prime of 0, negative cosine of 0 in this case, will be a negative 1. Well, in this case, it's asking us what are the values of a, b, and c going to be? And one of the things that we're, the tables themselves, I don't think they're probably the best way of demonstrating it. But essentially what we're trying to use the tables to illustrate is that f of x is equal to y, and f prime of x is going to be equal to y prime, and f double prime of x will be equal to y double prime, and so on. So when it says what are we going to get for the values of a, b, and c, we're taking f prime of, or f of 0 and y of 0, and we're going to set those equal to each other. So in that case, a is equal to 1. If I take f prime of 0, or f prime of 0, and it's going to be equal to y prime of 0, so b in this case is 0. And if I do the same thing, f double prime of 0 is going to be equal to y double prime of 0, so that means 2c. 2c is going to be equal to a negative 1, meaning that c itself is going to be negative 1/2. Okay? So the quadratic approximation, if I go back to, what I had here, and I'm not sure that's not what I wanted to do at all. I'm not going to be able to copy that, I guess. The quadratic approximation for cosine, meaning that, remember, f of x is the same thing as y. F of x, if I take the values for a, b, and c, and I substitute, if I substitute them into f of x, I'm going to get f of x to be 1, and so b is 0, so 0 times x is just 0. And c was negative 1/2, so I'm going to say minus 1/2 x squared, or if you prefer, x squared over 2. And so now I have a quadratic equation that, or a quadratic, function, polynomial, whatever you want to think of it as, that will be a much better representation of the approximation of cosine of 0 or cosine of x at 0 than what we would have gotten, with our line. So originally we had a line, looking like that, which was not a good approximation at all. But now if I were to sketch the quadratic, it's going to be much more appropriate as an approximation. And I encourage you, if you have a calculator handy, you may want to go ahead and take a look at it. So let's try graphing the functions here. So let's here we'll say cosine of x, and so there's the given function. And if I were to put in the polynomial approximation that we got to cosine of x at 0, I got 1 minus 1/2 x squared. And yeah, we can see at 0, it's a very close approximation, and we could zoom in on that if we wanted to. So let's do, I don't remember where zoom is here. View, no. Actions, no. Graph, no. Okay, there it is. I'm an idiot. Number 4. Let's just zoom in. I'm just not a very proficient Inspire user at this at the making of this video, but there you go. You can see that, yeah, at x is equal to 0, cosine of x and 1 minus 1/2 x squared, they behave very similarly. And that's the idea of what the Taylor polynomial is going to allow us to do. Okay, so let's see. Let me see if I can clean this up just a bit. Let's go back to the standard one, because I really don't like the thickness of the lines. Can I select what I want my window settings to be? So let's say from, I don't know, negative 2 pi maybe to pi on the x, or to 2 pi on the x-axis. There we go. That's a little bit better. Not so thick with the lines, and you can clearly see that, yeah, it does kind of give us a pretty good approximation to what cosine of x is going to be at 0. So let's go back and continue on with the investigation. So in the exploration, our polynomial approximation matched the value of cosine of x pretty closely. Its first and second derivatives at the center of 0 of x is equal to 0. Let's try to match more precisely, get a more precise approximation by using an even higher order approximation, meaning we want a larger degreed polynomial besides a quadratic. Now in the table, I'm not exactly sure that quadratic approximation should be what it said there. Maybe just Taylor approximation or polynomial approximation, because we're not going to be looking at we're not really going to be looking at a quadratic here anymore. In fact, if you notice what it's giving us, it's asking us to go down to the 6th degree derivative. So it's asking us to go to the 6th derivative, so that means I have to at least have a 6th degree polynomial here. So the first one that I would have, according to the pattern that we did for the quadratic, is I'm going to start with a plus b times x plus cx squared plus dx cubed plus ex to the 4th plus f x to the 5th plus g x to the 6th. And of course, the function that we're approximating at that point was y is equal to cosine of x. And maybe we need to pick different colors as we do these. I don't know. So the first degree, or the first derivative in this case, would give me b plus 2cx, just like what it did on the last table that we did. But if we keep going, we're going to get plus 3 dx squared plus 4 cubed plus 5 f times x to the fourth power plus 6g times x to the fifth power. And the first derivative here would be, again, negative sine of x. And you can kind of see, I think, how the rest of this is going to go. The next derivative is going to be 2c plus 6. Now, here, we can write it as 6dx, 6dx like that. But, you know, I'm going to come back to that here in a minute. I'm going to come back to that one because there's a point that I think it may make we can rewrite that one a little bit differently, and I think it may make a little bit more sense as we go through the investigation. But let's keep going. We can say plus 12 ex squared plus 20 fx cubed plus 30 g x to the fourth. Now, what I want to do, and let me pick a brighter color here so it's very distinct, the difference. Let me get something that I think you can see on your devices, whatever you're looking at. Instead of writing 6 dx, when I took the derivative of 3 dx squared, I could have written it as 3, oh, and I can barely see that. I'm not sure how it shows up on y'all's stuff when you're looking at it, but let's try this color here instead. 3 times 2 times dx instead of 6 dx. The 12 e to the x could be written as 4 times 3 e to the x squared. The 20 could have been written as 5 times 4 f x cubed, and the 30 could be written as 6 times 5 gx to the fourth. I'm not necessarily going to do that on all of them, but the idea, I'll probably do it one more for the third derivative, because the idea here, I want you to see a pattern being created that is something that the Taylor polynomial uses. And I don't want to spoil it, but let's go to the third derivative. So the next derivative, in this case, would just be 6d plus 24 e to the e times x plus 60 fx squared plus 120 g times x cubed. Now I want to, this will be probably the last one that I kind of write this way, just so that way we can kind of finish filling things in. So here, looking at the 24 e times x, we could have written the 24 as 4 times 3 times 2. I could have written the 60 as 5 times 4 times 3. And I could have written the 120 as 6 times 5 times 4. And I'm sure some of you looking at this are probably going to be able to recognize what the pattern is here, what that's called. But I need to go back. I forgot to put my second derivative here, and that's going to be negative cosine of x. And then we get this lighter blue here for the third derivative. So negative cosine of x, when I take its derivative, is just going to put me at sine of x. And when we get to the fourth derivative, let's just kind of keep filling these things in, I guess. Let's speed it up a little bit. Here I'm going to get 24 e plus, the next one will be 120 f times x, and then plus 360 gx squared, and this would be y fourth derivative. In this case, I'm going to be at cosine of x. And let's go ahead and keep going. Do I have any more colors I can pick from? Maybe that one. The fifth derivative will be, in this case, just 120 f plus, and then we got 720 g times x. So the fifth derivative here, derivative of cosine, in this case, will be negative sine. And at this point, we're repeating the sine, or the trig stuff. The trig stuff starts repeating itself at that point. And let's get one more here. Hopefully something a color that you guys can see okay. The sixth derivative will be 720 x, I'm sorry, not x, but g in this case. And so the sixth derivative here will be negative cosine of x. Now, what we're going to be looking at here is it's basically the same kind of table that we had before, where we just went through the second derivative, or through the second derivative, so that way we could find the values of a, b, and c. But in this case, we're going to start taking our pattern here, and let me see, match my colors here. So we had kind of that pinkish color, magenta or whatever that is. So here we're going to say f of 0. F of 0 in this case, again, just like it was on the previous table, is just going to be a, and y of 0 in this case is going to be 1. Now remember, this and this are equal to each other, because what we're saying is that f of x, whatever that we're having, is going to be equal to y. That's how we're creating these approximations. So in this case, a is equal to 1. And I don't think I want to buy. Sorry if I took too long with the colors. I just want to finish filling this stuff in. So let's say f prime of 0 in this case is going to be b. If we take the derivative of the, or if we just plug in 0 of f prime of x, everything's going to cancel out except for b. So y prime of 0, just like it was on the previous table, gives me a 0. And so in this case, b is equal to 0. F second derivative of 0 in this case will be 2c, and second derivative of y at 0 in this case is negative 1. So since 2c is equal to negative 1, again, c itself is equal to negative 1/2. Keep going. Of 0, and I'm going to get, here we had 6d, and I think you can kind of see it on the screen there. If I take the derivative of the next one in the table above, here y third derivative 0 is going to be equal to a 0. And again, you can really just kind of take the pattern with sine and cosine to see what the outputs are going to be. You know, the pattern 1, 0, -1, then you know the next one's going to be back to a 1, and so on. So here, 6d being equal to 0 means that d itself is equal to 0. And keep going for the next one, the fourth derivative. Fourth derivative at 0, in this case, was just going to be 24e. And the fourth derivative of cosine at 0, again, we can just kind of see the repeating patterns here. This is going to go to a 1. So 24e being equal to 1 means that e is equal to 1 over 24. And let's keep going. Can we fit it all on here? Fifth derivative at 0 will be equal to 120f. The fifth derivative of cosine at 0 will be equal to 0. So f is equal to 0. If I just say the 120f is equal to 0, that means f is going to equal to 0. And then finally, the sixth derivative at 0 is going to be 720g. So the sixth derivative of cosine of x at 0, in this case, will be a -1. So that means g is equal to a -1 over, and I kind of got the negative sign a little bit too close to my fraction bar, -1 over 720. Now, going back here, let's just come back here for a second. Specifically, I'm looking at these two bits here, the stuff that I did in yellow. What we're going to be able to recognize with the pattern, the way that I wrote them out is, 3 times 2 on the second derivative row to the next one becoming 4 times 3 times 2, and so on. What that is representing is a factorial, and I'm hoping that you were able to recognize that stuff. So here we can look at these. When we look at the values that we have for A, B, and C, we can start looking at those as factorials. So in this case, we're looking at the denominator, really. Let me go back to that yellowish or orangish color, whatever that is. We can look at this as 2 factorial. We can look at this, so 3 factorial, was just nothing. So this would be 4 factorial, and this would be, so 5 factorial gave me a 0. This would be 6 factorial in the denominator. And that's another way that Taylor polynomials are going to be kind of represented in textbooks or in math websites, things like that. So write the 6th degree Taylor polynomial, and unfortunately I couldn't fit it all on here, but we are able to take the expression 6th degree polynomial p sub 6 of x. In this case, all of the odd degreed portions of the polynomial worked out to be a 0. So I wind up with 1 minus 1/2 x squared. And then we say plus the 1 over 24 x to the 4th minus the 1 over 720 x to the 6th. Or if you prefer, you can write it kind of like this. You can say 1 minus x squared over, and you can write it as either 2 or 2 factorial, because 2 factorial is 2, plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, and you can kind of recognize that the degree of the x term and the value of the factorial in the denominator, you can recognize that they're going to be the same value. So when it comes to now here, let's go ahead and see what that looks like. Let's go back to the function here in the calculator. Oops, and my computer still thinks I'm trying to draw things. So let's get rid of that. Oh, I didn't want to, let's do tab, and let's get rid of this one. So we had 1 minus 1 over 2 x squared plus 1 over 24 x to the 4th minus 1 over 720 x to the 6th. And wow, that looks a lot like the cosine function at 0. Now you can see as we go further away from the center, the approximation clearly drops off. We can't really use it as we get further away from the center, but we see, yeah, we got a pretty good approximation there. And so the last thing that it's asking us to do, it says, can you, now that we've established a pattern for how we're going to be able to write the Taylor polynomials, could you do one for the 8th, the 8th degree approximation? So it's basically going to be the same thing that we had here. I'm going to just kind of take this and see if I can duplicate it. No, I don't see a duplicate thing. Clone, there we go. And with the alternating signs, this would be plus x to the 8th power over 8 factorial. And there we go. And if you want to type that one into your calculator, go for it and to see what the approximation, how it's going to change on the graph. Why is this important? What this is allowing us to do is really giving us a good way to approximate a function using a polynomial. And polynomials are always easy to work with. They're easy to differentiate. So here, this is what I have written down. We can differentiate. We can integrate. And approximate a polynomial much easier for a value at its center. Much for a value at its center. Now here, the center of the polynomial and the center of the cosine was at 0, but we could have done this very easily for centers beyond 0. And as we get into the next lesson where we're talking about Taylor polynomials in more detail, that's exactly what we'll do. But hopefully this sheds some light on where Taylor polynomials came from, what they're used for, and what you can expect to be doing with them as part of your calculus course. So thanks for watching, and take care and be good.